Hey, what's going on, guys? Mike again here. Last video I tried to make a video on how Bitboard is so great, but for some reason I started to talk about chess engine development philosophy, styles of coding and things like that. So I'm really sorry for that, and in this video I'm gonna actually I'm gonna describe what the Bitboards are and why to use them, the pros and cons regarding Bitboards, and I really hope that by the end of this video you would actually get an understanding of Bitboard. So let's start. Let's have a look at the chessboard that we have right over here. Right over in here, I've used. I'm sorry for the font is a bit little, so probably if I just make it a bit, so probably I can. So let's have a look at this chessboard representation here. So this is the bare text editor. So nothing much but the text editor. So here we got a chessboard with the Unicode pieces, this nice little cute Unicode pieces that they don't even need to represent the chess pieces because they are the chess pieces actually. So all the matter is try to give a computer some sort of an idea of how in particular he can actually store this board in its RAM memory. So it's a very simple idea. And well, for those of you who is not familiar with the array-based board representation, I highly recommend you to get familiar with that, because otherwise it would be a little bit too hard to understand the concept of Bitboards. But for those of you who don't really want to spend time on googling that on your own, I just want to show you the source code from one of the chess engines I've developed on this channel basically, and covered the most parts of it in the video in the video series. So here we got, so I hope you're familiar with the C programming, at least as a beginner. So here we got the array of integers. Doesn't matter that we have a double 48 squares, so 128, and that's because I'm using the so-called hexadecimal 88 bitboard representation here. But that's not the point. This is just needed in order to answer the simple question whether the target square the pieces go into is on board or not by a single bitwise operation, like to target square bitwise ended with the constant of hexadecimal 80. That's it. So anyway, you see this little letters here, so saying like rook, knight, bishop, queen, king, pawns. So lower cases are black pieces, upper cases are white pieces, and all these characters represent integers. So here we have the O, which stands for off board, and here we have E, which stands for empty square. And if we just have a look at the enumeration of these pieces, then we'll see that here they are basically. And if you're familiar with the C enumeration keyword, so what it does basically, so it assigns value of 0 to E, value of 1 to pawn, value of 2 to knight, and so on and so on and so on. So these letters are literally integer numbers. So we could have say like 1 for pawns, 2 for knights, but it's incredibly hard to keep track, to remember that in mind, all those encodings, and eventually you can get completely lost with that. So it's easier to represent them as this like constants, to visually see like where the knight is, like where the pawn is, either it's a black piece or white piece. So this is kind of it. But when it comes to the evaluation, it starts getting incredibly expensive to evaluate the position when the board is represented as an array of integers. So this is the starting point to introduce the concept of bitboards for you guys. So the idea of bitboards is literally the same as the idea of array-based board representation in terms of storing your data, but the difference is that the array is a kind of set of separate integers, while the bitboard is the set of separate bits. and that's the whole difference. Very, very, very simple. So obviously you know that even though we can give a layout to this array, so visually it looks like a chessboard, like like it's square. Even you can even ignore this right part. So let's say it's 8 to 8 board array. Even still, it's from the computer perspective. Obviously, it's not a square, right? It's kind of not even a two-dimensional array, which is also possible in C, by the way. But the two-dimensional arrays are even slower than the one-dimensional arrays. So that's the reason why people use one-dimensional arrays when they want to represent their board with their chess engine. So from the computer perspective, this is something like we get this line, and then we get this line. I just want to show you this. So this is one line, and then just up to right over in here. So this is one line basically. That's what we have. That's how computer understands this. And exactly. Oh my God, I'm sorry. And exactly the same thing happens with the bitboards. But the difference is that instead of using integers within the array, we use the bits within the single integer. So the same concept, but the scale is a little bit different. And so let me just try to minimize this first to give you an overall idea of this, and then I will probably be zooming in order to give a particular explanations. So but as far as within the single integer, so what we can see here is the bitwise representation of a given integer. So in order to understand whatever I will say further on, you need to make sure that you understand what the difference between the binary representation and the decimal representation. So I will now turn my magic calculator here, and let's consider the number of 1. It's quite pretty trivial. So if we have this 1, and I just go to programming mode here, so if we have 1 in decimal, and then let's say we want to see 1 in binary, no difference, right? So 1 in decimal, one in binary, they are literally the same. But if we just get back to decimals again and say like +1, sorry, not +0. Oh my God, how can I get rid of this? +1 equals 2. So now we have a look at this decimal value of 2 in binary. This would be 1 followed by 0. And just let's have a look at this. So that's the binary format. We have 1 followed by 0. If we have the number of 3, it would be 1 1. I will now try to explain why exactly this is happening, because this is absolutely essential to understand the concept of bitboards and why they're so cool. So let's go back to our decimal. So let's have another 1 here. So now we got this 3 in decimal. This would be 1 1. In binary, this would be 1 1. Okay, then if we just want to add one more to this, so let's say +1, and here we'll have 0 1 1 0 0 here. And I'll now teach you how easy it is to calculate this in mind, basically based on a very simple rules. So this is the number 4 in a binary format. And okay, just close. I just minimize the calculator for a while. So let's have a look. I'll probably need to provide some extra explanations here, so let's just scroll down a little bit. Okay, so now this is perfect. So if we have a set of bits, okay, like this, and now I just want to mention how much the current given bit is worth actually. So this bit is worth of 1, this bit is worth of 2, this is worth of 4, and this is worth of 8, then this is worth of 16, and so on. Just I won't be writing this longer, just so I hope you get the essence. And in order to convert this binary to decimal, so like this, so we need so say we have a 1 here, so 1 is worth 1, so in decimal this would be 1. And now let's say we have a number of 0 0 1 1. So how do you know what particular value this would be in binary? So we need to, so we see the value of this particular bit, what it worth. It worth 1, and then this one worth 2. And now as far as we know the values, how many, what kind of number it worth, we can just add them. So it would be 2 plus 1, so this would be equal to 3. So this is it. And now let's say if we have just this like we see this is the only bit here available, so we have it just equals to 4, and that's it. Quite pretty straightforward. And let's say we have all the ones. This means that we need to add 1 plus 2, this would be 3, and we need to add 3 plus 4, this would be, oh my god, this would be 7, right? And 7 plus 8, this would be 15. So we have this 15 being encoded, not encoded but represented as a binary number. So bitboards are the well, they are not integers. They are known as the unsigned long data type in C. I will now explain what does that mean. But literally, the bitboard is just an integer number. And if we have a look at the bitboard as the integer number, it doesn't make much sense. Like, say we have this bitboard equals to 15. We have no idea what does that mean. But if we have a look at the bitboard in the binary representation, and we assume that zeros represent the empty squares while the ones represent the pieces available on the current bitboard, this starts making huge sense to us. So bearing this concept in mind, we'll go further on. So the next thing to consider, it's a very interesting stuff regarding the computation in general, basically. So introducing the 64-bit architecture of the processors, let's us to operate with 64-bit long integers within the one, I don't know how to say this in English, I'm sorry, but tact, probably, if I can call this tact. Sorry guys, just I need to Google, by the way, my previous video is uploading to YouTube now. So I just want to, okay, I just want to translate this. I'm not exactly sure how this is about to be. Let me just, so just how this is supposed to be translated. Yeah, tact, this is it, perfect. So it fits the only single processor tact. Well, maybe the specific, there is more specific word in English language regarding this processor related stuff, but unfortunately I don't know that, if any. So this doesn't really matter that much, like how the computer operates this, but it means that the number, so now another little thing here. So let's consider that we don't have, so right over in here, let's consider we don't have all this sort of a numbers kind of at all, right? And this means that the biggest, so if say we have only 4 bits, right? Only 4 bits, that's all we have. So in order to so the biggest number we can store using this 4 bits would be 15. And also there is a little trick regarding binary numbers. I can't exactly say, I don't remember by heart at this moment. I need to Google a little bit, and I don't really remember how exactly it works, but they use a single bit to represent the sign, whether this is the positive number or negative number. Well, probably this is the the leftmost bit. I'm not sure. I might be mistaken. So, but this is not the point. This doesn't matter from the bitboard's perspective. This is just how the computers represent integers. So, we can so within the 4 bits, the biggest number we have is 15, and probably assuming that this is an unsigned value. Yeah, because if we want to say minus 15, probably, I'm not sure, but probably we need one more bit to represent whether this is the plus number or minus. But as far as that, I don't really know that for sure. I won't be really talking about this. So, but this is a little bit too little, really, right? So, imagine how big the number can be if we have up to 64 bits to make use of. So the biggest number would be like all 64 ones. So we need to say, so in order to realize how big it would be, we need to add 1 plus 2 plus 4 plus 8, so 15, again plus 15, oh sorry, no, not plus 15. So this one would be respectively like, so they would be like 1 and then 2 and then 8 and then 16 and then 32. Oh sorry, I missed 2 here. 1 2 4 8 16 32 64 148 256 and so on and so on, until there would be up to 64 digits in the row, and then we would just add all of them. That would be the biggest number that can be represented by the unsigned integer containing 44 bits inside. So now again, like the very important point regarding unsigned stuff. So in C programming language, it's called like unsigned long, like this. So this is how to define the bitboard in C programming language, but it's not a topic now, so let's try to make it free from the programming languages itself, basically. So what I want to say that if all these zeros would be ones, this would be incredibly big number, and whatever okay, just how to say this from the computer perspective, this 8 to 8 bitmaps are considered to be just a big integers, well, unsigned long integers, so 64-bit integers basically. But from the chess engine's perspective, what really matters actually is that we can use a single integer in order to save, in order to store the position for all current pieces of a given type and of a given site at the same time. So let's break this into parts, and again, like trying to understand like what's going on here. So okay, I just want to minimize this. Okay, but hold on a sec. Why oh my god. Why is this? Okay, my bitboards are too big for some reason. Okay, if I just save this, I'm sorry guys, I just try to reload my bitboard txt file here because something is going really wrong with this. Okay, thank God now it's much better. So let's take away so this is the starting chessboard position. Now let's take away, like mentally, all the pieces but leave only the white pawns on board. So there is we can create a one single integer that would represent the position of all white pawns on the chessboard, and that's the trick. So here how the white pawns position would look like basically. So all this one, so this is like a chessboard, and we have this bit's been turned on in order to represent the position of white pawns on the chessboard. This is it. So if we just encode this, binary representation into a decimal, this would be just a big, really big number, but it doesn't really matter how big this would be. This would be just a one single unsigned long integer. That's it. So we have one bitboard or one integer to represent all the white pawns on the chessboard. Then we go to the white knights. So here we have this bit. So let me just minimize this. Oh, this I see. This is the trick. He just probably okay. So let me just he can minimize. He can minimize the selection. Whoa, what a nice feature! I didn't know this is possible actually. Whoa, this is. It's always cool to know something new about your code editor. So here we have the bitboard for white knights, and we have only these two bits being turned on as ones. So that represent this knight and this white and this knight respectively. So I hope this is quite pretty clear. And this might be represented as another number, right? And then we have the same for bishops. So the bishops are over in here, and the same for, okay, let me just take it away. So the same for a king and the same for a queen. So this one represents the position of white queen on the chessboard, and this represents the position of the of the white king on the chessboard. So now I just want to ask you a question. How many bitboards we need in order to represent all the pieces for all the sides on a chessboard? And the answer would be 12. And this is why. So we have one bitboard for white pawns, one for white knights, one for bishops, one for rooks. So just probably minimize this again. One for this one's still big. Oh, what a trick! But doesn't matter really. So one bitboard for white pawns. This is one. Another one for white knights. Another bitboard for bishops. Another for rooks, for queens, and one more for kings. So six bitboards to represent all the white pieces on chessboards. And again, like by saying bitboards, I mean unsigned long integer data type that consists of up to 44 bits. So this is kind of it. And unsigned means that we use, if this was a signed integer, we would be able to cover only 63 bits. But to make it possible to set or get or do something with all the 64 bits, we actually need to define exactly unsigned long. Well, this regards to the C programming language, at least that I was working with and implementing this stuff in C programming language, obviously. So we have the 6 integers in order to represent all the pieces. And now let's compare. So if we just have this, okay, just let's search for our board array. So here we need, well, let's even drop this 64, even though they're absolutely essential, but let's just drop them. So let's say we have 64 integers to represent the entire board position, or we need only 12 integers to represent the entire board position. And this is really, so 12 is really less than 64, right? And also bearing in mind that we may use really tricky techniques during the move generation in order to make it kind of it's not always faster, but well, still it's a little bit faster compared to the array based, but even more we can do during the evaluation, which is a different topic that I will cover definitely, but just a little bit later on. So the very first thing I would like you to understand is actually how exactly the number of bitboards, or the number of this unsigned long integers. So we need 6 to represent all the white pieces, and we need 6 to represent all the black pieces. I didn't provide them here, obviously. They would be literally the same, but well, probably I can even do this now, I guess. So let me just try to close this and open again. Okay, so if I just grab this, copy, and just paste this in, so here we can say like have this white pawns, and let's make it like this. So white pawns and all this stuff, and all the pieces, and here we have the black pawns. So let's reset this back. So here, so now I'm doing something that is done implicitly within the chess program during, say, initializing the bitboards, or when you incrementally update them, that happens. So something similar is happening. So here we have the black pawns. Here we will have the black knights right over in here. I will zoom this when I'm done, I promise. So the same for bishops. Well, let me just reset them first completely, and then just go into setting up them. So the bishops would be here and here, the rooks would be here and here, and the queen would be on D square, and the king would be on E square. Safe. So let's have a closer look to this. Okay, so the idea that here we have the white pawns being set up, here we have the black pawns being set up. The same for knights, for bishops, rooks, queens, and kings. So overall, the number of 12 bitboards we need in order to represent the entire board position. Also, we need the variables to represent the side move, the castling rights, which are encoded in binary in a tricky, interesting way as well. But it doesn't regard to bitboards already. Then peasant square is something that we need to encode as well. But obviously, okay, guys, just hold on a sec. I get a message on my smartphone. Okay, sorry guys, sorry for being distracted. Unfortunately, I've completely forgot what I was talking about. Probably about bitboards, right? Just some issues, some daily issues here. Okay, so so yeah, probably we have stopped at the stage where we need up to 12 integers to represent the entire board state instead of at least 46, at least 64 integers in order to represent the entire board position within the array-based representation. So now the most interesting thing about bitboards is actually to maintain all these 12 bitboards along the process of playing the game of chess, basically. And this is a little bit not that easy, really. So now I just want to cover some tricks regarding how to actually move the pieces within the bitboard. So if we have the array-based board representation, then the matter of, say, putting the pawn from E2 to E4 is just the matter of well, in this case is the matter of subtracting the offset from the index of where this pawn stands, and subtract minus 32, assuming that we have this 128 board representation. So let me just show you this on the example of moving pawn from E2 to E3, basically. Yeah, so let's go subtracting. So subtract. So if we want to move this pawn one square ahead, we need to subtract the offset of 16. So in order to get from this index, get this index, right? So we have this index, but we need to get this index, so we need to subtract 16 from this index. So let's do this manually. So minus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So now we got here, right? And if say we want to move this pawn here, we need to add the offset of 16. So we add 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 and 16, and that's it. So the same way we can calculate the offsets for the knights to go from here to here, from here to here. So the offset would be, so if this is 16, this would be 17 respectively, right? This would be 15. Well, but not 15. It would this is for pawn capture. So here we have the 15. Here we have the 17, and for knights we need to actually add 32, and then add 33 or 31. That's kind of it. But it doesn't matter really. So there's the matter of either adding or subtracting the fixed constant offset that represents that actually converts the rule of how the chess piece can move on board into some sort of a mathematical expression, basically. But we can't do addition or subtraction on bits, right? But we can do something even more interesting. We can do the operation that is known as the bit shifted. So in C programming language, it's done using this sort of a command. So this means to shift the bits. So let's say we have this binary representation. So let me just zoom in a little bit. So we have this 1000, which is in decimal would be equal to 8. And if we just want to say move, let's imagine that this is the rook, or even let's go to the rook bitboard in this case to make it even more clear. So here we got the rook. Okay, so here we got the rook. So let's say we want to move this rook from here. We want to move it right over in here. So in order to get this position from the initial position, we just need to shift all the bits. Well, not all the bits. We just need to shift. We actually need to shift this bit 3 bits to the right. So it was right over in here, and then just goes right over in here. And again, if we want to move the rook back, we just shift the rook back. I'm not going to be diving into how it is implemented in C programming language at this moment, but I just want to introduce the concept of actually being able to shift the bits, and this is very this is a very important concept. And I mean, like another little thing here that I did, I wasn't very accurate when describing the bit shifts. So no, it's not exactly like this. Okay, let me just fix this before we go further on. Actually, to be absolutely exact regarding the bit shifts, we can shift. So yeah, now let me actually show you this. Well, say we have some sort of a number here, and let's say like this. Okay, so say we have this number, and now if we do this bit shift, it would shift all the bits like this. So it won't be doing this separately. It would be shifting all the bits. So this is a little bit different technique, but we still can calculate the offsets for bits. And by the way, well, let me actually try to Google for the bit shifts. I should have done this before this video, because I wasn't doing bitboards for quite a bit of time, for about 2 years, I guess. Bit shifts, maybe here in Wikipedia. So I just really want to. Okay, bit shifts. Arithmetic shift, bit addressing, left decimal plus 23, left minus shift. Well, okay, so I really need to yeah, I need to recall my memory because I don't really remember, guys, how exactly this is done. I'm really sorry for this. I just can't recall my memory how exactly this is about to be implemented. I can even show you the source code, quite pretty rare one that where I was implemented the Bitboard mode generator just just to prove the fact that I was actually doing this. And here is the entire mood generator. So quite pretty lots of quite pretty lots of stuff here, and we have really lots of things here, and probably it won't really tell you that much, but anyway. So here's the parse FEN for the bitboards and things like that. So anyway, the idea is that we actually can switch the bits from the source square to 0 and the bits of the target square to 1, and imitate the piece movements in that sort of in that way. So that's the core idea. So as far as in array-based chessboard, we can just use the index offsets. Here we can do literally the same, but we're using the bit offsets, not the index offsets. Yeah, probably the index offset was the right word I was about to pick up there. So now from now on the idea is very simple. We just need to maintain the entire chessboard position state within these 12 integers by actually moving them back and forth during the move generation process, and that's it. And then we can make use of this bitboards for the evaluation purposes. And I remember I promised to tell you this. So without going into the great details, so now regarding the evaluation, what I want to say that as far as every single bitboard is just a single integer, we can perform some bitwise operations on it. And if we bitwise, if we perform some bitwise operations between the current given bitboard and some sort of a bit map, we can do a really fast evaluations of location of bits. And again, like, without going into the great details, we can using the bitboards, say for pawns, we can distinguish between double pawns, isolated pawns, those pawns that are about to be promoted, so kind of getting the pawn rank and things like that. And it's really faster with the bitboards compared to with array-based chess engine, with array-based board representation there. And the only thing that I want to kind of try to explain regarding these masks, so here we have this off-board mask, and now let me introduce the one of the main issues within the move generation in chess programming in general, regardless of either whether it's an array-based chessboard representation or a bitboard-based. So let's consider that we have a pawn, and it can take, so let's consider this one. So let me just maximize this, or even let's go to my this cube board representation here. So let's say we have a pawn, so it can go either right over in here, if there was an enemy's piece, obviously, right, or it can capture like this. But the problem is how to distinguish the off-board captures. So how to avoid pawn capturing off the board. So this is the exact behavior that we actually want to avoid. But assuming that the nature of the board in the computer perspective is like this. So we have this like going one by one. So assuming this nature. Okay, so now just to show this exactly precisely. So we're trying to capture, well, let's say here we got this. So this pawn would be this pawn, right? Well, probably it would be better to show with the black pawns, I guess. Yeah, let me better just, I'm sorry guys, let me just better show you this with the black pawns. It would be more visibly clear, like, of what's going on and what am I talking about. So just put the pawn back. So we have this line of, and then we have this line, copy, paste. So we have, so this line is right over in here. Well, let me actually even put this pieces to make it even more clear, like what am I talking about. So yeah, okay, and well, let me just minimize the camera for a while. And so here we have 8 pieces. Okay, I've never been I've never tried to explain this before. What I want to say, that if the pawn captures, say, right over in here, then it would appear well, for about right over in here. But I'm just now trying to calculate the exact place where the pawn would appear if it captures off board, assume the 8 to 8 board representation. So this was a little spoiler, but now I just really want to recreate this. Well, let's get rid of some unnecessary pieces here. So 0, 1, 2, let's say like 0, 1, 2, 3, 4, 5, 6, 7. Okay, so 5, 6. I am now naming the indexes 8, 9, 10, 11. So let's give them a bit of more space. Here we have 12, 13, 14, 15, and here we'll have 16, and here we'll have the 17. So that's what I mean. So you remember, like, I've been explaining that when the pawn wants to, well, this 17 of sets is right for the hexadecimal 88 board representation. But so now let's try to calculate the offsets for 8 to 8 board representation, because these are the exact offsets that we would be facing during dealing with bitboards. So in order to put the pawn from here to here, we need to, assuming that the index of 0 starts here and the index of 44 ends right over in here, we need to add 8 to the current given index. So add 8 to this index in order to move this the pawn 1 square ahead right over in here. And in order to capture, we need to add either 9 or 7. So let's try to add, yeah, I don't even need this. I don't even need this. So let's just try to add, so it can capture here, it can capture like +7, but it can't capture here. So let's add the offset of 9 to this point, to this point. So 1, 2, 3, 4, 5, 6, 7, 8, 9. It would be right over in here. So if the pawn, if this pawn would try to capture off board like this, okay, so let's just imagine, so this pawn is trying to capture off board. Obviously this won't happen, because from the engine perspective, this is the single line, right? Regardless of whether we're talking about the array based or the bitboard based board representation. So in the array based representation, this like capture would put the pawn right over in this position. because from the computer perspective, this this line starts here, right? Because we just add these new lines here just for the more readable representation from the human perspective. But the offset of 9 is exactly right over in here. You see, like 1, 2, 3, 4, 5, 6, 7, 8, 9. So starting from here, we're actually having this stuff. So either the pawn would be placed into the wrong place, or even if here for some reason we'll have some sort of a white piece, and this might occur a horrible bug, like pawn, if it just tries to capture from here to here, which is impossible. It would actually eventually capture this knight, which is absolutely weird. But this is the exact behavior that would happen if we don't have the appropriate logic to forbid the pawns going off board. And when we were dealing with the array-based chessboard representation, we had a trick. We could say, like, if not square bitwise ended with the constant of hexadecimal 88, like this, sorry. So we could use this simple expression to avoid this disaster that I've been just showing you, like capturing off board. But how can we do this assuming the bitboard representation? So in bitboards, we agree, initially we agree that pawn actually can go from here, right, to here. But what do we do here? So we don't forbid pawns capturing off board. But as far as well, pawn from the pawn bitboard perspective, it can't really capture anything. So in order to make sure that the capture is happening, we need to compare the pawn's board, the pawn's bitboard, and the bitboard for a current given piece that this pawn is about to be capturing, say a knight. But from the pawn's perspective, say we trying to capture from here to here off board, this would result a bitboard like this, and that's kind of it. So okay, is this yeah, I really hope yeah, I really hope that it was actually correct. But now I feel a bit confused about my, hold on a sec, I feel a bit confused about my off-board explanation here, off-board mask. So the idea is to is just to a bitwise end, or hold on a sec, probably is this gonna be all once instead of, okay guys, I was doing this so very long time ago that I don't even remember. Yeah, probably I didn't even save, yeah, I didn't save these masks, so unfortunately, oh yeah, I really should have prepared better for this video. So if we just perform the bitwise AND operation between the resultant bitboard and, yeah, so if we just say, okay, if we just say 1 bitwise ended with 0, it would be equal to 0, right? If we say 1 bitwise OR with 0, it would be equal to 1, right? Okay, so we need to reset this. We need to reset this bit back to 0. So how to make it? Okay. So if we so what value do we need to bitwise AND this pawn with in order to reset this? We need to bitwise AND this with a 0, right? But I'm just wondering, is this pawn gonna be resetted, gonna get resetted as well? Or if we just Guys, I don't remember. It was so long time ago. Oh my god. I'm just wondering, is it gonna look like this actually? Okay. I'm not sure. I don't remember. Or I did use the XOR for this sort of a purpose. If I could only remember how exactly this is about to be done. The idea that some sort of a bitwise operation was actually used in order to just fix this bit back to just to erase it back, so it allows to make an offboard move, but it is always trying to fix this sort. Okay guys, hold on a sec. I think I got I know how I can extract this. So if I just go to my I just need to find the square attack function. Okay, it should be right over in here. And the pawns. Okay, so black pawn attacks. Hold on a sec. So this should be black pawn attacks. I just so where do I have this? They are the constants. I remember it for sure. They are the constants, but where are they stored? This was about 3 years ago. I don't already remember it completely. Okay. Or is it called a mask? Clear mask. Bishop shifts. Oh, this is it. Not H file, not GH, not yeah. These are the guys. Okay, so not a file. This is it. I just want to see the particular. I just want to see the particular number for it. It's getting initialized somewhere within these files, but if I could only remember where exactly that was happening. So find place. Yeah, this is it. So yeah, we're doing this. Yeah, so like yeah, we're using the bit shifts. By the way, yeah, we're using the bit shifts, as I was already mentioning. Okay, and not a file, but where is this not a file being defined? Okay, but hold on a sec. Maybe just it wasn't defined here. I mean, this is defined, but where is this getting initialized? Maybe here. Paste. So do we have this? Oh my god. That's what's happening. I'm sorry. When you're coming back to the 3-year-old code of your own self. So no, it's my Okun. Not a file. Not a file. This is the variable, but it should get initialized somewhere. Okay, probably it would be faster to find this on chess programming wiki. This might be the case. Okay guys, so let me just try to find this pawn bitboards chess programming Wikipedia. Obviously I didn't actually invent this on my own. It was pawn attacks. Yeah, this should be right over in here. Captures. Okay, yeah, this is it. This is it, guys. Yeah, this is it. Fortunately, So yeah, actually my assumption was correct. So not a file. This is how we called. Yeah. So my assumption was correct. You see, like, I still remember something from the Bitboard stuff. So yeah, this is it. And then we just like it happens here. Pawn attacks, pawn attacks here. So we just making this offset either to 7 or 9. Regardless, depending on color, it either left shift, left bit shift, or right bit shift, and then we just need to bitwise AND the resultant bitboard with so not we're not bitwise ANDing the bitboard. We are bitwise ANDing. Well, I'm not. I could only remember which in particular this from square stands for. From square, it starts from, it's actually 0 and sign lon. Okay, set bit from square. Oh my god. Okay, so let's not dive into the implementation, well, at least for now. So the idea is, if we just yeah, probably we bitwise AND this not a file bit map with, not a bitmap like a picture, but the map of bits basically. When we are bitwise ANDing this with a pawn that will get here off board, so all the pieces would those that would get bitwise ANDed with 1 would remain 1, but those that will get bitwise ANDed with a 0, so those pieces that not those, but that only pawn that would be occupying the A file, it would eventually would get turned into a 0 back. So that's kind of it. And again, all this stuff is already kind of implementation dependent stuff, obviously. And again, like when I would be making videos on how to actually generate these pawn moves, obviously I would recover this in my memory, and just I would know this for sure as far as when I would be writing some code. But for now, just everything I remember so far is about to be presented to you guys. So that's just the general kind of direction of where to go. So we're using this bitwise AND operations, using this sort of a maps in order to make sure that pieces or any other pawns won't really go off board. And obviously we'll have the structures like this to make sure, like say for knight is not going either left or downwards. So depending on the bit shift, we need to specify the appropriate maps for every single direction, so to make sure that the piece is not gonna get off board. But again, all this stuff is already an implementation part, which is not obviously the topic of this video. So I just wanted to give you a quick example of how one should think when working with the bitboard. So it's all about bits, bit shifts to move the pieces, kind of okay, again, like I don't really remember if we move the pieces using the bit shifts, even staring at my own code, believe it or not. So I don't remember what. So the opponent blockers is the bitboard. So we also have 2 additional bitboards. We need 2 additional bitboards up on top of this 12. So one would be all the white pieces, and another bitboard would be all the black pieces, and we will using them in order to make sure that you're not capturing your own pieces, and to make sure that you are capturing the opponent's pieces. So the representation itself, the representation of board using the bitboards, is not that difficult itself. The most challenging part is actually to unite all this stuff into a one particular implementation that would allow you to make your engine actually generating moves. So that's the most challenge eventually. And that's and as far as we also, you know, like we will need really lots of functions to set bits, get bits, shift bits, functions to define the attacked squares. I'm not sure if I'm gonna be creating this. So we can. So here it's probably, oh my god. Here I had it's this pawn attack bitboard. Oh my god, I don't remember. I don't remember what I did here. Oh man, there has to be a function called is square attacked. Is square attacked. Maybe it's not even here. Oh, okay, this is here. I'm sorry for this weird coding style. I had no idea about the good coding style at that time, so I'm just using the camel case and then this. I mean, this is really weird, but that was my code from for about 3 years ago. So here I'm doing this. I'm calculating that if square attacked by the given side on the fly, and I'm not really sure. Yeah, probably I'm doing this on the fly. Yeah. Okay. Try to stop making a smart face while examine my own code. Okay, so that's better. Drop back to our bitboards. So I don't know whether I managed to explain how bitboards work or not, but at least I tried to give you an experience, give you this feelings of what you need to take care of while working with these bitboards. And in the practical parts, in the practical videos, I would obviously be already assuming that you understand that the concept behind bitboards. I will obviously say like that we need up to 12 integers in order to represent the bitboards for every single piece, but without this visual understanding it would be probably a little bit too hard to understand, even though I would probably be providing this schemas within the source code in the commentaries to still kind of to make it even more clear, like what's going on there basically. So yeah, probably that would be a good idea in general. So yeah, I think this might be a good idea. And what about my plans? So well, I hope the concept of bitboards is now clear. The pros of bitboards is in theory they are faster compared to array-based board representation used within the move generators, but it's in theory. On practice, it's really incredibly hard to make a bitboard chess engine work faster than the array-based, because so many pitfalls available there. And for me personally, yeah, as I was already mentioning, that the very first attempt to create a bitboard move generator, actually I made a for about 5 times slower move generator involving bitboards compared to the one that I made before using the array-based move generator board representation. So that was quite a bit of pain. Another pro is that we can make use of bitboards during the evaluating the positions. To be honest, I've never been doing this before, because my experience with bitboards actually ended where so I just made a move generator. I did pass the perf test, got the correct results, and was satisfied at that point. So I didn't really continue developing that engine. So you see, like if you have a look at the source code, we have everything but not search and not evaluation, which is the core part of whatever chess engine. Just have this the bare mood generator, and that's kind of it. And I did even maintain the Windows version being cross-compiled on my Linux system. So these are the pros. So it's faster mood generator if if you're smart enough, which I can say about my own self, and that in theory it should be way easier to evaluate the positions. And the cons, so some bad, some really some kind of downsides of this approach, that as you've already seen, it's incredibly difficult to maintain this 12 plus 2-bit boards to represent all the white pieces and all the black pieces on board. So it's incredibly hard to maintain, and the matter of answering like what actually what piece is E4 square is currently occupied by is a real pain, assuming the bitboard board representation. So in the array-based board representation, you can just reference the board array using the index that is responsible for the coordinate of E4 square, and it's not really that easy on using the bitboards basically. So we also need to provide some extra logic of mapping all this bitboards together. And again, the way I was doing this, I was mapping this just again into the array-based representation, and I was maintaining and incrementally updating that array during the mood generation process. And I don't really remember at the moment if there is an opportunity to avoid doing this, because it would be really cool to have just the pure bitboards without any arrays representing pieces. I don't remember if I did research this earlier. Even if I did, I didn't I didn't really understand much of that. So that's what I'm supposed to be researching from now on, because this is really interesting here. And also there is some difference regarding hashing the positions. By hashing I mean assigning the unique value of a relatively big number to a given position by XORing all the pieces and the square they occupy, and the castling right in the peasant square, and what else? Something else probably. I don't remember. Again, like, because I wasn't ever yet implementing this hashings, and this unique IDs are needed. Would be needed later on when one day we would like to implement a transposition table, a technique that actually allows us to store the moves that we're searching within the search. So to avoid search exactly the same positions again and again, and that's the principle of transposition in chess. That means that you can actually reach the same position using the different principal variations. But in case of the chess engine, you can it's not even the matter of different principal variations, it's the matter of a really number of combinations of moves that eventually would lead to exactly the same position. So the idea is, if you have the current position already stored within your transposition table, that means that instead of evaluating it, you can just use the pre-stored value for its evaluation, for example, or maybe some other parameters, if any are needed there. So that's kind of it. So and again, like the way how we will hashing our positions, assuming the array-based board representation, and the way we're supposed to be doing this using the bitboards is different. I'm not sure how exactly at this moment, so I didn't yet research this, but I think that probably it would be even easier with the bitboards, because the bitboards are integers themselves. So probably this would be slightly easier, but I'm not really that sure about this. So anyway, this is something to mm, to make a video on here on YouTube. So yeah, so the cons that actually it's incredibly hard to maintain this. But again, another pro here that actually when you're dealing with the array-based mood generators and board representation, the problem is that your engines are doomed to be limited by the estimate elo strength of for about, well, maybe 2300s, maybe even 2500s if you're very smart. But if you just read the history of development of well-known chess engines, every chess engine, every famous chess engine has this like story that it has been used in the array-based board representation until it reached the elo of say 2200s, 2300s, and then we needed to completely rewrite our mood generation logic, and we switched to bitboards in order to make the evaluation better and things like that. So with a bitboard chess engine, with a bitboard mood generator and the chessboard representation, the potential elo strength of the chess engine you're working on is not limited like it is in terms of the array based. So this is the very last benefit probably of this bitboard stuff here. And now let me say just a few words, just a couple of words regarding the further plans. And this would be a little bit of lyrics probably and philosophy as well, but still, let me just, as far as I already did cover the bitboards, let me just say a few words regarding some future plans. So how I personally observe the reason of why to do chess programming in general and why to do bitboards in particular, that's chess programming is some sort of a human activity that allows you to reveal such a deep features of your own personality that you could never have an idea of the fact that they even exist. Oh my god, yeah. So researching how this techniques and technologies works involves you to dive into your own nature, into your own self, and it's incredibly interesting. So when you have some experience, not only as a developer but as a human being, basically, when you have some experience, when you just gonna feel some patterns that serves as the guidelines for your own life, it's quite pretty natural to have a desire of trying to apply a desire of applying these principles to whatever activity you're currently producing, basically. So the same with the chess engines. So the matter of it's all the matter of implementation. And again, like what I was talking about in the previous part, where I tried to talk about bitboards, but eventually I was talking about anything but not bitboards. So as I was already mentioned with the previous part, that it's easy to follow somebody's tutorial, but even if you succeed while following that tutorial, you won't get satisfied, because you will realize eventually that having the result of a working chess engine that by the first time it seems like the main goal, but later on, if you realize that it's not really that big deal to create a working chess engine, and if it's not even a big deal to create a strong chess engine, even though I've never created this chess engine stronger than 1600s elo points, but even still, the matter of strength is just the matter of the number of applied techniques. So the more techniques you master, the stronger your engine would be eventually. And it's not a point to make it. The point of satisfaction is reached when you understand what actually needs to be implemented, and when you find your own way on how actually this is about to be done. So when you find your own way of how to do things, of how to implement this, and that is something that is really satisfies you. So that's the exact reason while you're covering this bitboards, I will try to I will be doing two things simultaneously, just two things. So the first thing I will start development of a new chess engine. Well, probably I would be reusing my Wukong chess engine, the current one that I've been working on, that I created in order to make the hexadecimal 88 board representation series on the chess programming channel, and also some stuff regarding the Nigamex alphabet search algorithms with the move orderings. I didn't yet implement the move orderings, but doesn't matter. So probably I would reusing the code from this engine quite significantly, I guess. But probably I would be reusing the search part. Well, I'm not sure at the moment. Maybe I will rewrite everything completely. It's not the matter of getting a result. It's the matter of following the flow of this internal process that is initiated within inside you when you're writing a chess program. That at least to my understanding, that is like that. So this is the first thing I'm supposed to be doing, and even though that I was covering some the state of the development progress regarding my Wukong chess engine, I probably won't be doing this regarding this new chess engine that probably would have the same name. Actually, I'm not sure, because nobody really cares about this. That's the main reason. But at the same time, I will try to highlight the core gist parts of the bitboard board representation and the mode generation along the way. So this knowledge, in theory, in my dreams, they should be enough in order to generate your own chess program. And again, instead of maintaining one piece of code and adding some new parts every single next video, which might be annoying for those who don't really want to follow the entire series but want just to get some gist regarding some particular specific part of the bitboard implementation. So bearing this in mind, I would be trying to create a one piece of code per one video, and this piece of code would do some little task like, I don't know, like set bitboard or get set bit on the bitboard, get bit on the bitboard. Like defining the bitboards would be nice to make. Would be worth of making every video, I guess, even though it's some sort of a duplications. But my YouTube experience on my other Komaki Kings channel that regards to web scraping and web development clearly shows that when I'm creating a web scraper hundreds of times, then eventually subscribers starting to realize that, okay, we need to make HTTP GET request, and then we need to parse the response, and then we need just to store the this data structure that we've created by extracting the data from the HTML response to the CSV file. Okay, so there are exactly 3 steps to consider, and if you're just trying to explain this in theory, they don't understand. So they just understand that only if you're making this 100 of times, and they're watching this 100 of times, and then they suddenly realize, okay, so yeah, we just need to make a request, then just to extract the data, then just to store this to the output file. So that's how it works on YouTube, at least in my experience, in my YouTube experience. That's how it works. So I'll probably try to follow this concept and follow this principle within this bitboard related stuff in the chess programming. Well, guys, so this is it from my side. Those of you who has watched this video until this part are real heroes. So I really appreciate you watching and listening to my to my stuff here. So thanks a lot. Thanks for following. Thanks for watching. And I really hope to give you some interesting insights regarding the implementation of Bitboard, board representation and mood generation stuff as well. And what is really interesting regarding the Bitboards that it's kind of modular itself, and it's kind of, you know, like well, I don't even know how to say this, but maybe just this is just in my dreams. Okay, so I just need to stop this because this video is never gonna end in the in other case. So yeah, thanks for watching. Until the next time, and see you next video. Take care, guys.